multiplies your signals that you transmit. All right, so I need to expand this, maybe the view. So probably you could also refer to the code that you have, which was shared. So if whatever is on my screen is visible to you, here is a case where we have a BPSK modulation system. Here we are talking about binary phase shift keying. So binary phase shift, I'm not able to use my tablet at the moment. So binary phase shift just means that the two symbols are actually 180 degrees out of phase. So if you have a sine wave, one of them will be a sinusoid. Let's say you have a sine wave which has a zero value at 0 degrees, and at 90 degrees is maximum. So if you have that kind of wave for the first symbol, then it means the other symbol would also have 0 at the beginning, but with a -1 value at 90 degrees. So they are 180 degrees out of phase. So that's what we call BPSK. So when you transmit those symbols to a receiver that is noisy, sometimes it's very hard to detect the symbol that was transmitted, because the one that is 180 degrees out of the phase may be changed to be the other one due to noise, because noise is a random value, n. For example, you have this n here. So the received signal is what we call y. But what is received is actually h multiplying the x, because this is what you transmit. So let's say your x is a -1 or a 1. Then n is random. We don't know what it is. It's just some energy at the receiver in your circuitry. So you may realize that you transmit an x that is a -1, but when you add n, let's say n is 2. So if you transmit x being a -1 and n is actually 2, then you will actually see y as a +1. So that would cause you to choose x as if it was a 1, as if the transmitted symbol was 1, because that's what we are seeing at the receiver, and yet it was -1. So noise actually causes a lot of errors, and it's a random value which is centered at 0 mean with the variance 1 for the additive white Gaussian noise. That's what we said, how we define n here. So we can say it is a WGN. Some noise here. If the path that is used for transmission is just noisy and there's no fading parameter on the channel, then we say that h is equal to 1. So for purely noisy signal, what you're going to do for purely noisy signal, we'll have something like that. So that's purely noisy, so h is equal to 1, so you can remove that. Then so this is purely noisy. This one has fading, so the channel is fading. There's a fading in the channel, right? So fading means then the energy is being lost and your symbol is actually fading away, losing energy. So whatever you are receiving is also not x, it's a modified version of x. But if it is just purely noisy, we are going to see the difference in the simulation for the two. All right, so that is the received signal. So you transmit x, but as it passes through the channel to the receiver, there's a channel impulse response there, h, which modifies whatever is going to be received, but you're receiving y. And as you sample that signal, it gets some noise that is added onto it. So that's what you are supposed to declare there. Then for programming purposes, we clear everything else before we start. So here, for us to really get a good average, because what we want to determine here is the number of errors in a random, noisy environment. So if you just have one symbol that you're transmitting, you may receive it in error or not in error. So for you to get a better average, you can try like 100,000 symbols. So that's why we have 10 raised to 5. So those are number of bits or symbols that we are transmitting. Then we'll get the average number of errors out of that 100,000. Then at the transmitter, what we are trying to do here, at the transmitter, here the input here, IP, is equal to random 1 up to 100,000, because that's what n is. We have declared n here, which is what we have on line 24. So what this does in MATLAB, if you say rand 1 to n more than 0.5, so it's going to generate random values between 0 and 1 with equal probability of 0.5, zeros and ones. Because we know BPSK, either you're transmitting, the information that you have sampled is actually zeros and ones. So we're just putting random values up to that number. But now we perform BPSK modulation. So the first box is just sampling and quantizing, and then now you do the modulation. So when you do the modulation, you can decide and say you want to transform zeros into all the 0 bits. You modulate into -1. All zeros, change them to -1. So it means that when you have an input 0, then you get the wave that has a peak of -1. If it is a 1, then you get the wave with a peak of +1. This is just what you decide, so long as the receiver knows this is the decision you have made in your modulation. Otherwise, you could also decide that a 0 is a +1, it's a physically wave with a peak of 1, and a 1, you say, is the one that has a peak of a -1. So long as the receiver knows that, it will be able to demodulate back. So that's the modulation point. For this one is simple for BPSK. You can have for 4 QAM, for 4 bits, for 2 bits, for 4 symbols, or 16 symbols, 8 symbols, 32 symbols, 64, 128, 512, 1048. It just depends on how you write your program. So this is how you modulate. So we are saying S, the modulated symbol, is equal to 2 times the input random bits, zeros and ones. So here, can somebody tell me the value of S if IP is equal to 0? What will be the modulated symbol? Perform that modulation for a 0 input.
-1.
Yes, for a 0 input is -1, and for a positive input, 1, for a 1.
One.
Yeah, for a 1, it's a 1. So you see, that's the modulation that we have here. We have decided to do it like that, so there's no big deal. Then addition of AWGN, noise at the receiver, should be AWGN. Now, we know that the noise that we want to plot, that we want to use, has a PDF whose mean is 0 and the variance of 1. That's the PDF that we want to get. So how do you generate it? Now, MATLAB has a function called random n. So if you have rand n of those values, it will give you random values that if you plot their PDF, then you get a Gaussian PDF. So rand n will give you those values. So they're just some random value. Let's say we can put just 10 values. So we can put n is equal to 10 raised to 1. I just want to see this random value. So what I'll do, I'll open this. Then you say plot n, plot n. So let's just run a small code there and see the plot of n, because we want to see those random values. Yeah, so you can see, it's not, I can say grid on. can put figure 1. Yeah, so you can see the random values. Let me remove the lines. So you can see the random values. You see, and noise can be almost -1 in the first one. It can be 0.5, maybe 0.2, or negative 0.09, or negative 2.5. You can see how random they are, okay? So these are the random values of noise. So you can't really tell what noise is. That's why we normally have errors at the receiver. We can do like 100 of them and see. So you see how noise happens. You right see. So the first transmission, the noise is small, negative 0 point maybe 2. The second one, negative 0.3 or 1. The third one, noise is 1 point something. You can see that. So it's quite random. Such that if noise is 2 and you had sent a -1, if you sum those two, it will give you a +1. You think that the signal that was transmitted is a 1. You shall have made an error there. So this is how random noise is. So if we plot the PDF of these random values, we will get a Gaussian, right? So that's what we are trying to say there. And that is important for us for propagation. Okay, so that's I wanted you to see that, so we can comment out that one. You can do it at your own time. Then now I have to, because if you don't have this semicolon here, then if you go to the window, command window, you'll find those numbers there. You see, it will fill up your window with all those numbers. So the semicolon then closes this output. Right. So that's how random the noise is. So we are dividing by √2 according to MATLAB, because it's a complex number. So according to MATLAB definition of that function rand n, you have to divide by √2. Then that's now we have prepared the symbol that we want to transmit. We know how noise looks like. It's a random value. Each time you run it, it will give you random values. Then now you have the signal to noise ratio. At what power are you transmitting the signal? So you also have to evaluate that. So this is energy of the bit which you are transmitting to noise ratio. This we are preparing it in decibels. So 0 to 10 decibels. So those are multiple of signal to noise ratios from 0 to 10. Negative, a 0 dB does not mean a 0 value. Okay, 0 dB is actually at 1, meaning the noise power is equal to the signal power. Then, so we have now, this is just programming. So we want to test from one symbol to the, here we had 100,000 symbols. And then we also want to test from 0 dB, the whole length of the dB range, SNR range, that's the signal to noise ratio range. So that's just for programming. So you say for I is equal to 1 to the length of that. We say that Y is equal to S is the modulated symbol, that's what we are transmitting, plus the noise. But now, here, what do we have here that is pre-multiplying noise? That just shows that each time we transmit at a certain signal to noise ratio, if you increase that power, then the noise power actually is going lower as you transmit at a higher SNR. So that's why we are saying this is just for programming purposes. So we're saying you change it to the decibel, you change it into decimal. The decimal, you change it to decimal. So if you have SNR in dB, we know that is equal to 10 log to base 10 of SNR in decimal. So what is SNR in decimal? So SNR in decimal is 10 raised to SNR dB over 10. So that's what we have here. So you have to change it to decimal because we're working in decimal values. So we want to see how does that then affect the noise. So the more you increase the signal power, the noise power goes down. So that's what we are trying here. That the scaled noise, which we call sigma, is going to be, scaled noise is going to be scaled by a sigma, which is this. We normally have sigma, which is the power for, there in this case, the standard deviation of the noise. So we calculate sigma as 1 over square root of that SNR in decimal. So you must understand that why we are doing that. So that is what we have here. So 1 over square root in decimal is the same as 10 raised to minus EB in dB divided by 20. This 20 here, if you divide by 2, just means the square root in dB. If you do a square root in dB, it means in decimal you divide by 2. Okay, the power. So that's the calculation that you are seeing here. So that's all. So we have added noise and at different signal to noise ratios. That's what you do. Then now at the receiver, you have received Y. Y is the modulated symbol S plus noise. Now this is called hard decision decoding. Probably you have done that in the telecom side. I don't know which semester you did. So hard decision decoding means that whatever signal that you receive, you are going to select, check if the value of that signal is more than, we can also plot Y so that you see. If the value of that signal is more than Y, is more than 0, then you say a Y1 was transmitted. If the value is less than 0, then you say that most likely was a -1. I hope it is clear. So we can have another figure too. Here we are interested at Y, in Y. So we are saying you have received Y. So hard decision decoding here, you check the real value of Y. If it is more than 0, then you will conclude that the symbol that was transmitted was a 1. But if it's less than a 0, then you conclude that what was transmitted was a -1. You know that is not always true because the noise can be bigger than 1. So it means if the noise is bigger, then you are actually decoding in error. So our decision will give you more errors. But let's see what happens on Y. Figure to plot that. Let's plot Y and see. Right. Here, according to that noise, you saw that our noise is actually a complex value. Let me show you. You see noise, so Y that we're going to get is complex. You see noise here, N is rand N plus J rand N. So N is complex. But we know that the symbol that we are transmitting is 180 degrees out of phase. So we don't care about the complex, the imaginary side. So we can just choose the real side only for this case. But if it was Fockwam, we have to use both because normally Fockwam is a complex number that we use to determine the symbols. But for BPSK, it's just a 1. So it's just a real value. Okay. So let's see. That's why we are saying real. Some did come. Let's see command window. Figure 2 is not generating. Okay, so that's the figure 2. So some fall on the positive, but you see they're just falling around +1 and -1. Okay, so it's around +1 and -1. So anything that is So what we are saying is that anything that is near a positive 1, we decode that a 1 was transmitted. If it is near a negative 1, we decode that a negative 1 was transmitted. So you can see that's the kind of signal information that we are receiving. And this is due to propagation in the channel there. No channel, we have no problem because h is equal to 1. This is just due to noise. We will also look at when h is not equal to 1. Okay, so we go back to the data. Then, so you here is hard decision there. The other way you can do equalization is by maximum likelihood decision. In that case, you see y is equal to s plus n. So you can generate a function n1 and n2 because you have for a 0 like here. If a 0 was the symbol that was to be transmitted, which is into a negative 1, so it means you had y is equal to a negative 1 plus n1. Let's say if 0 was to be transmitted, then y0 would be that. Y due to 0 transmitted would be minus 1 plus n1. So here you can write that n1 is actually equal to y0 plus 1. You see that? So n1 is that, if a 0 was the one transmitted. I hope you're following. What if a 1 is the one that was transmitted? Sorry. If a 1 is the one that was transmitted, you'll have y1, whatever you receive, is equal to 1 plus some noise, n2. In this case, what is n2? So n2 would be y1 minus 1. So this is another way of detection called maximum likelihood. So what you do, where you form a function for the noise. Okay, if a 0 was transmitted or a 1 was transmitted, so whatever you receive as y, you can add 1 to it. Then for n1, and then whatever you receive, if a 1 was transmitted, for n2 is equal to y minus 1. Then you square it. So this value of noise, so you check between noise 1 and noise 2, because you have only received y. But the only possible values that might have been transmitted is either 1 or a negative 1. So you check which ones among those two noise values is minimum. So you check the minimum noise. This probably you have done. So you select which one is minimum noise. So you have this function here, n1 and n2. Then now you check the distance between that. Distance is the noise, then the position. The minimum one, is it n1 or n2? So if it is n1, you can see. If it is n1, it means a 0 was transmitted according to our equation there, because we are adding. You see, it's y plus 1. If it is n2 that is minimum, then we know that a 1 was transmitted. So that's another way of detecting. So you get your distance and then the position. Then now you demap. You say for k is equal to 1 up to n, for position kk is equal to 1, then it means the estimated value of the input is a 0, isn't it? Because we are saying if n1 is the one that is minimum, because we remember we are finding minimum from this equation here. So minimum n1, n2. So if the position is 1, the first position, then it means then a 0 was the one that is transmitted. Else, the estimated input is a 1. So after you get all those values, then now you compare, because you know IP, the input. So here you are going to check. So there's a comparator where you're checking the input versus the estimated input, which we are calling input with a hat. The estimated value, we normally put a hat on top of some symbol, isn't it? So IP and IP hat. Now that is maximum likelihood detection. Then you can also do soft decision, log likelihood ratio. So you do a log likelihood ratio. It's the same, only that now you're adding some additional information. You are saying now you want to get the logarithm of the Gaussian PDF itself. So instead of just N1 and N2, you are going to put the Gaussian exponents, exponent N2 and exponent over exponent N1. So with that, then you check the likelihood ratio. That's the soft decision. So if the log likelihood ratio is less than 0, then you say that the estimated input is actually a 0. But if it is more than a 0, should give you, if you modulation were higher, for BPSK, you may not see much difference. But if the modulation were higher, like FOCWAM 16 and those higher modulation schemes, you realize that the way you detect now, the soft decision, because of this more further information here, will be able to gather more intrinsic information and the errors will be lowered. I hope that is clear how telecom comes into this work here. So we are not going to concentrate there in the decisions. We just want to see, after you find that, now, you see, remember you have two vectors now. The input, this one you have, this is what they decided as random numbers, zeros and ones, random zeros and ones with equal probability. But now, your output here of the recorder gives you the IP. So if we just remember, if we are using the soft decision, I've said it is called IP hat 1. If you're using the here the hard decision, we just call it IP hat with the ML. So it depends. So we can call the first one here, yeah, the first hard decision we call IP hat 2. Here, ML we call IP hat. So it means these are 3 decoders. So you can only use one at a time according to this program. So whichever you choose. The values will be computed. IP hat 1 is for the log likelihood ratio, the soft decision decoding. So what you're going to do, you are going to check what distance is the shortest. So you're asking between zeros and you compare the input, which is IP zeros and ones, then you compare with the IP hat, the values that we have gotten from the decoder. So we can just have a look at just 10 of them. What we're going to do is what we can do, let's compare. So let's have IP without a semicolon, then IP hat. We just want to see what values do we compute at the end. Just 10 of them. So we look at the command window. You see, so the input was 00111 01100, but our output 00111 01100. So there's no error. So that one we have computed without error. It means the signal power is so high, so we can check somewhere because it's giving us the last value, which is 10. Let's say at 2 decibels. Let's see the output. It's good to compare them within one bracket. So we can say IP hat. Then we can do that. Here we just want to check the output. When the numbers are few, you can always do these checks as you do your programming. You just lower the number of symbols you're testing. So we compare IP and IP hat. So you just go to the command window and check. You can see answer is the same. So even at 2 dB, we have the same. I want a point where there are errors. Let's try another one, just in case. Let's go to command window. Is it really changing the randomness? Those are too few for it. Let's see. Go to another power, lower power. Let's do at 0 dB. 0 dB noise power should be the same as symbol power. I'm not seeing there. It's calculating them correct all the time. What about yeah, now you can see at -4, the output has error. So the input is 00111 01100, but the output is 00111 010. You see, so we have missed the third last symbol. We think we have decoded it as a 0, and yet it is a 1. Then the second last also we have decoded as a 1, and yet it is a 0. So there are 2 errors out of 10. So the error rate, bit error rate, is 0.2. Okay, I hope you're getting now the sense. Okay, so I think that is clear. Any question before we go to look at the bit error rate for the whole, for a longer period? Anything you didn't get? So you can do that through simulations. Now this we can block because it's going to give us some outputs there which will slow down the program. Any question? So this is just theoretical analysis. Whatever we are doing in simulation, that where we are putting random values, actually there's also a theoretical function called Q function. This you probably learn in at master's level, I think. So if you have a Q function of these values of the SNR, you can actually have the same curves that you get when you do the simulations. Okay. So that's not for you now. Then you just plot now. You plot the bit error rates, then you compare with the theory functions that are known on literature. So when you run this, it should just give you the answers. Okay, any question up to that point? So this case is where we don't have, it's just random noise. So here we just have random noise. Additive white Gaussian noise. I hope you saw how random the noises were. We can also do you have seen the noise, so we don't have to do the PDF. So now we can run and plot and see the average value for 100,000 symbols, and then you average out of that. So all the errors that we measure, the places where ones and zeros are not equal between IP and IP hat, that's what we are counting with this statement here. The number of errors is equal to the size of the places where IP is not equal to IP hat. Then you count. Then that's number of errors you divide by the total bits that were sent. So this is the average. So if the more you send, the better the curve that you get. So let's now send 100,000. There we are. So I should have closed figure 2. You know, figure 2 now is trying to give us all the random values, 100,000 of them. Didn't close it, so it's fine. Now we have this. This is the one we are looking at. This is the bit error rate versus the signal to noise ratio, the energy of the bit to noise ratio in dB. So the simulation is the one in the blue curve, and then the theory is the positive one. Another theory about. We just need to see that whatever we simulate is correct according to the theoretical equation. So you can see that the bit error rate compared to, again, it's the signal to noise ratio. What it's telling you is that at -4, you have like 2, that is 1, 2. There are going to be 2 bits out of 2 bits in error. At 0, 0.9. Okay. Then let's say at 10, the theory is lower than the simulation. It just means we need to do more because we only did 100,000 symbols, so we cannot be accurate anything below 10 raised to negative 5. That's why you can see theory saying we should fall there, but the simulation is falling at 10 raised to negative 5 because those are the symbols we have. But if we simulate 10 raised to 6, then we'll be able to get this other one. Yeah. So this is the curve. So it means by that standard, this is how this curve must appear. So if you can come up with a way of doing that BPSK modulation, which is different, that takes this curve to the left, meaning lower errors, then that becomes a patent and maybe goes to 6G or something like that. So we expect that this BPSK is the least, then FOCWAM will be here, 8 and 16 going away with more errors because you have more symbols that are near one another. So I hope that is clear. So that is for the noisy channel. What if we have a fading in that channel? What if we have fading? I don't know whether I sent you for fading as well. Probably I did. Let's see if it opens. So Safin, you have two codes in that file, in that document.
Yes.
Okay. So you have fading as well. All right. So here we can do 2. Actually, it's good to just do the 2 and compare them together so that you see when there's fading and when there's no fading, which one has more error. So this one has H there. Let's do this quickly and see. 10 raised to 6. That one will take forever. Let's do 10 raised to 5. Change that. Okay. All right. So probably this, you get the difference. You saw that we had around 10 raised to negative 5, about 10. So this blue one, if you are able to see it as blue, the first one on the legend there is the AWGN, where we only have noise at the receiver. But if you have a fading interferer in the channel, which is multiplying the symbol itself, H times X, and H is also random just like N. By the way, the distribution of N is the same as the distribution of H. So H is also a Gaussian random variable, okay? And it's complex. The complex nature of it does not affect the BPSK because BPSK is just one. You either transmit in the real or in the orthogonal. There's no sum of both real and quadrature. So H here is going to affect that symbol in a way that now you can see the red one is in theory, but in the simulation is the Rayleigh fading. Rayleigh fading where is H is distributed according to a Gaussian random variable, but you have a complex value, which we have seen. If you go to the editor, you see the definition of N is the same as the definition of H. You can see that. So it means the distribution is the same. 0, mean, variance 1. But now the equation for the received signal is now here. Y is equal to H times S plus noise. So that's the difference. Okay, everything else is the same. Here we are doing hard decision. No, so in equalization, what you do when you receive the signal, so the estimate of Y, you just remove the H. Okay, you can see here Y is equal to HS plus N. So you remove the H to equalize so that it looks like as if there was no fading, as if it was just noisy. So this is what we have, okay? In generic form, y is equal to hs plus n. So what you can do, you can say y that you're estimating is equal to, if you divide by h, so you'll have s plus n over h. But because the distribution of n and h are the same, you see, n over h, it will just be another random value which is complex, isn't it? But you see, you have it in the form as we had before, s plus some random value which we can consider as noise. So even this one we can consider as noise. But this noise now is more complex than the randomness is now not Gaussian as the other one. It has Rayleigh effect in it. It has Rayleigh effect, that noise. So that's what is now leading to this kind of erroneous output. So there's more errors when there's fading. Okay. So that's why when it's raining, the absorption would cause such a problem, or the scattering that happens due to obstacles on the path. And you can see the difference between a fading channel and an unfading channel is over, let's say, almost over 30 dB when you look at 10 raised to negative 4. Okay. So that is it. So what we'll be considering this semester is the difference between the blue line and the fading channel. So that's why we will be designing the link so that we try to push that fading channel as much as possible towards the blue line. That also you do in telecom using coding. We have just seen there. You can now test the hard decision. You can test the maximum likelihood. You can also test the soft decision decoding and see whether those lines move towards the left. So that in telecom side. But on propagation side, when you are setting up your link, you must also make sure that these curves fall within this blue one and the red one. So that's all it is. So this is the end game. But now we'll be looking at how do we get here using our devices and also skills in link planning. Any question up to that point? Are my students in class? Yeah, almost all of them. All right, guys, so we stop there. I go back to Senate. There's a meeting going on. So you can put in your attendance.